This is example 5-10 siphon hose. So basically what we have a reservoir up here, the blue one right there, and then we have a hose that sits in that little, I guess it's a river, and then once we start water flowing, it will keep on flowing even although it has to go uphill first and then goes down, right? That's the idea of a siphon. Now in our case, we are asked what the volumetric discharge is at C, right? So what's the flow in the hose? Of course, we know that if the hose has a constant diameter, right? It says 50 millimeters. We will know that the velocity in this hose has to be the same everywhere, right? So it doesn't matter where we find our velocity. We will know what the discharge is. We're also asked to find what the lowest pressure is. Now we can already say, right, if we are going to think about what the lowest pressure is going to be, well, the velocity is going to be constant in the hose, so that means the pressure is going to be the smallest, where the elevation is going to be highest at point B. But we'll get there. I think we'll start to find what our flow rate is. So we will use Bernoulli's equation going from point A, let me get a red color, which we'll say is somewhere here on the surface, down to point B at C, where we have an outflow. All right, so it's water, so that's good, right? That means we're an ideal fluid, and it's steady flow, so that's good. And we can say we're on one streamline, right? We could go from A down into the hose, over the hump, down to C, right? So that's all going to be one streamline, which means we can use Bernoulli's equation. So if we write that from A to C, then we'll get PA divided by gamma plus VA squared over 2G plus ZA is equal to PC over gamma plus VC squared over 2G plus ZC. All right, so now we have to go through and eliminate or figure out as many of these as we can. Let's start with the elevations. That's often the easiest. So we will set our datum to be right down here. All right, so we can say datum at hose outlet. There we go. All right, so that means my point A at the surface of the river, right? We know that the top of this hill is 8 meters from our datum, but then we go down to the 2 meters. So our ZA is going to be 8 meters minus 2 meters, 6 meters. That's our ZA. ZC is, of course, at the same level as our datum, so ZC equal to 0. That's always good. We like to have zeros, make our equations easier. What else can we say? Maybe the pressures, right? So we see that both point A is at the surface as well as C is at the atmosphere. So we can say, maybe we'll start just for point A. Point A at surface of river. That means that's if it's in contact with the atmosphere, right? Atmospheric pressure means gauge pressure equal to 0. And then we can say point C is free outfall. All right, that means the water is just flowing out there. It's not flowing into anything. Free outflow, which means it's in contact with the atmosphere, which means PC is also going to be 0. All right, so we already have 1, 2, 3, 4 knowns. That leaves us with 2 unknowns, VA and VC. Now, VC is the thing we're trying to find. That means we have to figure out something for VA. In our case, we can say, right, our velocity is going in this direction, but it's a big river, so we can assume this is a reservoir, right? So we can say point A at surface of, well, I guess we'll say it just like above, of river, right? That means it's moving very slowly compared to what's moving in the hose. So we can assume that VA is equal to 0. Let's go to that next page here. All right, so if we use all these and stick them back into the Bernoulli equation, then we would get 0 for the pressure, 0 for the velocity, but we do get an elevation, so ZA. And then at C, we get, again, nothing for the pressure. We get the velocity that we're interested in, VC squared over 2G, and we get no elevation. Well, it doesn't get much easier than that, right? So we can say VC is then, of course, just, we don't even have to bring anything, just multiply by 2G and take the square root. So it would be 2 times G times ZA, and the square root of that. That would be our velocity. Plug in some values here, right? So it'd be 2 times 9.81 meters per second squared times ZA. If we go up, almost see it, right? ZA, that was the height difference going down to Z. So that'd be 6 meters. And if we plug values in, that gives us 10.84988 meters per second. And then we're not asked for the velocity, we're asked for the volumetric discharge. So of course that's just Q times A times VC. Don't have to really say AC, right? Because the diameter of the hose is constant. So all we have to do is do pi over 4 d squared times VC. That would be pi over 4 times, see how big the hose was. The hose was 50 millimeters, so it would be 0.05 meters squared times 10.84988 meters per second. And that gives me 0.0213037 cubic meters per second, or 2.13 times 10 to the minus 2 cubic meters per second. Right, so that would be our volumetric discharge. That was the first question that we had to answer. Now the second question that we're supposed to answer is what the pressure is at the lowest point. Let's go back to our figure again here, right? So where along here is going to be the lowest pressure? Well, if we think about our Bernoulli's equation, right, we know that VA, or that the velocities are going to be the same. Right? So that makes no change. They're going to cancel out. So that means we only have the change in pressure versus the change of location. Right? So that means the smallest pressure is going to happen at the location of the highest difference in height. In our case, highest point is point B. So we can go through the whole thing again now with point B. Right? So we can write Bernoulli's equation again. We can say PA divided by gamma plus VA squared over 2G plus ZA is equal to PB, which we're looking for, over gamma plus VB squared over 2G plus ZB. All right, so we already know that PA is equal to 0 because it's at the surface of our reservoir. We already said that we figured out what our velocity is, right? Because the velocity at C is going to be the same as at V. Well, let's write that down maybe, right? So we have constant diameter hose and incompressible fluid. Right, that means the volumetric discharge is the same everywhere, and it means that diameters are the same everywhere, which means that the two velocities that we have, VA and VB, are all going to be the same, right? So we know VA is equal to VB is equal to I already said C, times VC. You can give the number there, 10.84988 meters per second. All right, what else? So we have the V's. So all that's left are the Z's. ZA, we already have. We choose the same datum as before, right? ZA is going to be 6 meters. Then we can find ZB. Well, let's just note that again here. Datum through point C. All right, that means my ZB is equal to, all the way up, right, that'd be 8 meters. So we 6 at A and 8 at B. All right, I think with that we have all the information that we could want. So we can plug that back into our equation. We get 0 for the pressure at A, 0 for the velocity at A. We get our elevation at A. We get the pressure at B over gamma, right? That's what we're looking for. And then we get the velocity at B, which we figured out what it is, divided by 2g. And of course we get ZB. All right, so let's solve this for PB over gamma. It means we have to bring all this stuff over, but we'll have ZA minus ZB, and then minus VB squared. So if we look back to VC, VC was 2 times G times ZA in the square root. So if we square that, let's write that down. Maybe make it very clear here. All right, so that was just 2 times G times ZA, all that squared, over 2g, and the ZB we already have. All right, so that would be ZA minus ZB minus the square kind of cancels each other out. 2 times G times ZA over 2 times G. So we get ZA minus ZB minus ZA is equal to ZB. All right, but we're not looking for a height. We still need to multiply this all by gamma to get our pressure. So PB, and I forgot a negative sign right here, right? Because like ZA is positive, ZA is negative, but ZB is negative as well. So let's not forget that. So we'll get minus gamma times ZB, which means we're getting a negative pressure. All right, so that means we will get minus 9,810 Newton per cubic meter times, what was our ZB right there? It's 8 meters. That means, plug that in, we get minus 78,480 Newton per square meters, right? Because it's cubic meters and meters. We can transfer that straight to Pascal. So that would be minus 78.5 kilopascal. Right, so that's the pressure that we get at the top of the hose, right, at this point right here, which is a negative pressure, right? So it's kind of a suction more than a pressure. All right, we're also asked to draw the energy and the hydraulic grade lines. See how much space we have. We'll start right here. Right, so we talk about our energy grade line, or EGL. Right, so what can we say? Well, we know There's no pumps in the system. There are no turbines. No turbines. And no frictional losses. What does that mean? Means that we get a horizontal EGL. All we have to do is figure out what at what level it is. So what we can do, we can just write E, and we can choose any point. Let's just do point A, for instance. PA divided by gamma plus VA squared over 2G plus ZA. Well, we know pressure is 0, velocity is 0. That leaves us with 6 meters for the height difference. So overall, my energy grade line is going to be at 6 meters, ahead of 6 meters. Now, just for the fun of it, let's make sure we get the same value everywhere else. All right, so if we put it at point B, over gamma, it'd be B squared over 2G plus ZB. So now, of course, we do get a pressure. All right, we figured out what the pressures are up there, so it'll be minus gamma times ZB over gamma. That was our pressure. Then our velocity at B is the same as velocity at C. Right, so we see the same thing happens here. So we'll have 2 times G times ZA, all that divided by 2G. And then our height was going to be, our height was at ZB was 8 meters. Or just leave it as ZB, I guess. All right, so if we look at this now, I get these gammas here cancel out. My 2G cancels out. So what am I left with? I'm ZB plus ZA plus ZB. The negative and positive of the ZB cancel out, so I get equal to ZA, which is equal to 6 meters. Excellent. Now for the last point that we have, we'll plug that in too. So we can say for E at point C, right, we'd have PC over gamma plus VC squared over 2G plus ZC. What do we get there? Well, we get no pressure at C. We get our velocity, so VC squared over 2G. And we get no height. So that means we get 2 times G times ZA divided by 2G. Everything cancels. So we're left with ZA, which is 6 meters. So that's good. So we found that, as we'd expect, the energy is the same everywhere. So now let's figure out the hydraulic grade line. So let's see here. Hydraulic grade line, HGL. What can we see here? Well, we have a constant velocity in hose, means HGL is parallel to EGL. Let's write that a little nicer here. To EGL. At what level though? Well, we should be able to figure that out. So if we do H is equal to P over A gamma plus ZA, right? That's our definition of our hydraulic grade line, because we're just taking off the velocity term. Our case, that would be 0 plus 6 meters, which is 6 meters, which looks like it's the same as the energy grade line, which would be strange because we have water moving. So let's see if that is the case everywhere. So if we go to PB over gamma plus ZB, then what will we get? Well, now we do get a pressure, right? We said our pressure was minus gamma times ZB divided by gamma plus ZB equal to 0. That's a different value. Let's see our last point. PC over gamma plus ZC. Well, PC we said it was 0. ZC is 0, is equal to 0. So now what's going on? Why do we get two different values? Well, let's go up here to our figure and figure this out. So the reason why we get a different value at A is because A is not in the hose. Right? So we said that we get something that's parallel because the velocity is constant. Well, the velocity is constant inside of the hose, but our starting point A is not in the hose, right? So the velocity is going to increase from point B until it gets to the inlet of the hose, at which point it is the velocity that we calculated, right? So we'll have to draw something that starts at 6 meters but then drops down to 0. So let's draw that in here. Let's give us a little bit of a coordinate system, I guess you could say. So let's do a straight line at the bottom. Let's put some markers on there, right? So say we start at A. I guess B was not quite at the half point, was a little further off, and then BC. So A, B, and C. And then let's do the energy grade line, right? We said that was just a horizontal line. Oops, that's the wrong. There we go. Right, just at 6 meters, so something like this. There we go. That would be our energy grade line. EGL equal to 6 meters. And now our hydraulic grade line, right? We say it starts up here, but then it goes down to 0 when it enters the pipe, and then it stays, and the hose, I mean, and then it stays at 0. So we'll just put here EGL equal to 0 meters. All right, so now we have our hydraulic grade line. Oh, not EGL. 2 energy grade lines. That's not good, right? So this will be our HGL, our hydraulic grade line. So for our problem, we figured out what our hydraulic grade line looked like, what our energy grade looks like. We found that we have a slight suction, a slight vacuum, you could say, at point B, which was the point with the lowest pressure, and that we also found what the discharge rate was. Now, of course, it's important to know what that lowest pressure is, because remember, we want to make sure that we don't get cavitation, right? So we'd have to now go back and see what temperature the water is, and then we can figure out what the boiling point is, and then we could decide if this location is creating cavitation.